for coming to this presentation. My name is Roman. I work for a company called Pivotal. And today I will be talking to you about a bunch of things, all of them related to Cloud Foundry in one way or another. But most of them are pretty low level. It is in fact a talk about how we enable something like Cloud Foundry as opposed to like how do we use something like Cloud Foundry. So this is a plumbing talk, I'm a plumber talking to you. My qualifications, before I actually begin, consist of having a single patch in the Linux kernel and, hailing from the Plan 9 community, so I'm fully prepared to discuss any kind of operating system internals. So why do we all love paths? Well, actually, this is the kind of paths I like. But seriously, I mean, if you think about it, paths is awesome precisely because it lets us not worry about a bunch of stuff, right? Instead of, trying to figure out, what needs to be started in my data center, how do I need to configure a bunch of things, what package recipes do I need to use, all I do is just, CF push. And CF push makes sure that a whole bunch of things happen behind the scenes. I have these machines somewhere in the cloud. I might not even know which cloud, right? All I know is that my Cloud Foundry command line can talk to these machines and the right things happen. But what is the right thing? Well, the right thing is, I have my application and bits and pieces of that application get blasted onto a data center. They get instantiated and they start coordinating with each other and, some kind of a useful service emerges. And it's all well and good, as long as we're talking about the stateless services. But what about the stateful one? So I also come from the background of big data management, Hadoop, sort of ecosystem community. And the way we do stateful in that ecosystem is basically we abstract that state away. So it is a very similar model to what we all use with Cloud Foundry, but with one interesting aspect. So at the very bottom of everything, we have this, stateful management substrate called HDFS, which is actually consisting of individual services, providing storage capabilities to that substrate. And by the way, these services actually happen to be resilient ones. So this is an example of running something like HBase. HBase, for those of you not familiar with it, is, you can think of it as MongoDB in the Hadoop ecosystem. So the way HBase would run in a typical data center is sort of similar to how a CF push would, result in a whole bunch of activity in the data center. But the only difference being that the services that I'm running on every single node are essentially the servicing doing two things. So first of all, there is a service, abstracting away direct-attached storage and making it part of this whole substrate, right, HDFS. But then there is also a service that takes things that now reside in that substrate called individual regions for HBase and, serve them up. So what happens if one of the nodes fail? Well, if one of the nodes fail, then the coordination service that also happens to run in the same data center basically detects that the node has failed, rebalances the whole cluster, and by the way, because HDFS is fully replicated, we're not actually losing any data. And by the way, all of these little blocks, little regions that we need to serve up, they're still in HDFS, so the only thing that we need to do is rebalance what service is now serving better. And if the node happens to come back in, an interesting bit of HDFS magic happens that lets you reuse the disk that is now available to the substrate. So bits will be blasted onto that disk, replication will kick in. But from the standpoint of the services, again, the service basically comes up. It asks a coordination service, what am I? What do I need to do? Give me some work, and it starts doing that work. So this to me is both CF push and stateful services, and I would actually call this the microservices-based deployments. So people talk about microservices, what it is, and to me, this is what it is. So you have a bunch of things that are blasted on onto individual nodes in your data center. Those things happen to be resilient in the sense that if you kill one, the whole system doesn't go down. And in fact, if you listen to some of the Netflix presentations, they actually do that in their production data centers. So they have Chaos Monkey just randomly killing the services to make sure that, if a hardware failure happens, their system still keeps operating. So this to me is the definition of a microservice. Doesn't matter what everybody else is saying. Let's actually now ask ourselves a question of how can we build something like this, right? So obviously there is a whole bunch of magic, orchestration magic, that happens to make sure that these individual bits of functionality get blasted onto the nodes in the data center. So that is the bit that we will not be talking about. So there's a whole lot of interesting stuff happening at the orchestration level. But at the end of the day, what I'm interested in is once the rubber hits the road, once there is something that needs to be executed on each individual node, what happens then? So let's zoom in, right? Let's take an individual node and try to figure out how to best execute a particular bit of functionality on that individual node. So what is the anatomy of the microservice? Well, I would argue that every microservice that we manage looks something like this. So there is obviously sort of an application layer of the microservice, which typically happens to be a microservice code. So maybe it's your Java code. Then there is some kind of virtual machine, and I don't really mean necessarily JVM or anything like that. It can be just a virtual machine that interprets the code that you blast into the microservice. It could be just a configuration virtual machine. So if you have a configuration subsystem, think of it as a virtual machine. Then there's a whole bunch of stuff, and then there's hardware. So let's take a look at what this stuff is. Well, this stuff is actually very annoying. So what this stuff is, it's what we need for the virtual machine to connect back to the bare metal, because it just so happens that we've been conditioned that you cannot really run a virtual machine with bare metal. I mean, it's pretty much impossible. So we have to run some kind of a kernel, maybe Linux kernel. We have to basically manage a whole bunch of packages in the OS image, because apparently JVM has dependencies, so we have to lay those out carefully. We have to use something like Puppet or Chef, or maybe some of the other provisioning tool to actually manage those images. And finally, we end up with this huge VM image that is actually pretty bulky, so it's really difficult to lug it around the data center. And the question that I ask is, is there a better way? So to me, this is actually a way better way. If any of you at this point are just coming from another exciting conference called DockerCon, hold your thought. I have a slide to talk about what near and dear to you. Here, what I'm talking about is actually not Docker, although it looks quite a bit like Docker. So what I'm talking about here is that, well, why don't we actually reduce the amount of stuff that we have to put in that image to a bare minimum? So what could be that bare minimum? Well, ultimately what I really want to do is I want to run JVM on my bare metal. Well, that would be kind of difficult because, we have a host OS, right? So why don't we then use virtualization technique to actually accomplish that, but in a guest sort of VM image? So instead of using VM image or container that has a full-fledged operating system just for a single purpose of running JVM, why not create just enough glue to tie JVM back to the hardware? And a friend of mine actually has a good analogy. He's like, well, that would be like libc for bare metal. That is exactly what it is. So hardware, then you have some kind of hardware virtualization assistance solution, be it Xen, KVM, VirtualBox, you name it. Then you have virtualized hardware that is essentially given to the entire image of your application, and then your application runs. Now, is there any problem with that? We will actually try to figure that out. But before we do, let me give you a little bit of terminology that I found useful when I was trying to figure out this stuff. And by the way, this stuff is pretty recent, in the sense that I kind of sort of gave up on operating system design and operating system research after Rob Pike, famously declared that operating system research and system research in general is irrelevant. And I'm like, yeah, Rob, you're right. It's like I should not stop paying attention. But back in 2012, 2013, a whole bunch of interesting things have happened, which I actually had no clue about. Because my professor taught me about microkernels versus monolithic kernels. And that was a settled debate, with Linux, like we all know who won. And then it just so happens that my professor, forgot to mention exokernels and nanokernels, but those don't matter, trust me. What does matter though is unikernels and anykernels. So what are these? So unikernels, basically, to the best of my knowledge, can be traced back to the paper that came out of, I believe, Xen group, roughly speaking. So there's a University of Cambridge that does a bunch of research, and there's like a virtual Xen group that just does stuff with Xen. So at some point, they did this interesting paper on Mirage OS that I highly recommend everybody read, called Unikernels Library Operating System for the Cloud. It came out in 2013, and to me it actually defines sort of this space of like, wow, I didn't know that is possible. What it basically defined is a library operating system. You know, a novel concept that instead of using a kernel that multiplexes between different processes, basically serving as a arbitrator of hardware resources and processes, they're like, well, why don't we actually have a library that is kind of like a kernel, but in support of just a single application. So there's absolutely no multiplexing between, you know, different user space, you know, processes. Just a single process, same address space, same everything. Very interesting ideas. Unikernels is another such idea that sort of came out roughly at the same time. And any kernel is not even any kind of a kernel. It's actually a programming discipline. It's how you write a kernel. If you write it in a certain way, then you can call your kernel in any kernel. So Linux kernel, for example, could totally be written as an any kernel. It is difficult, so the only implementation of the any kernel today happens to be NetBSD, but I highly recommend reading this thesis by Andy Canty, which defines how to write a kernel in such a way that you can reuse implementations for all the bits and pieces that comprise a modern kernel. So you can extract, let's say, TCP IP stack and plug it into your application without changing, you know, much at all. So with that bit of terminology set up, let's actually look at something that is truly exciting for me. Because, you know, all of the stuff that I've talked about so far is research, right? You know, it's nice and dandy and, you know, generates papers and I guess, you know, provides tenures. But at the end of the day, I'm a technologist, so I want to run something, and I would like that something to be maybe a backend for Cloud Foundry. So I'd rather have something that people are actually seriously considering for production use. And it wasn't until, I would say, last year, that I was just like, well, there's nothing happening in that space. That would be productization of all these ideas. And I think it was last year when I first met guys sort of behind this project called OSv. So they form a cloud system, and, you know, two of them are present here. So Dor is sitting right here, and Don is sitting right there. And if you have any questions, you know, that are deep and meaningful, they're way better people to answer them. I'll just give you the overview.
Not sure, by the way.
But they are the group that is actually standing behind OSv, and they're actually the company that stands behind the OSv. And that is very different, you know, compared to all the previous attempts of doing something like this. So let's very quickly look into what OSv is and why it's so relevant to microservices architecture. So I'm not sure whether Dor would agree with me, but if I were to explain OSv in a single sentence, I would actually say that it's a unikernel for POSIX-like applications, and it is best suited for the memory-managed applications. I will explain why it makes sense, at least to me, but that's what it is. So it is actually also has some of the any kernelish features, because, you know, if you look into how OSv is implemented, and by the way, OSv is not a derivative of any existing kernel. So it's not a Linux derivative, it's not a BSD derivative, it's a written from scratch, you know, bunch of code. But it also leverages some of the existing technology, for example, ZFS for file system management. And the way that it leverages ZFS is any kernelish-like, because they don't actually re-implement ZFS, you know, the way that Linux, for example, tries to. They actually leverage it from OpenSolaris, I believe. And it's kind of like a code import that is very much any kernelish in nature. So they're trying not to get into, you know, like managing ZFS bits themselves. So it runs on top of KVMs and VirtualBox VMware. In fact, it's running, you know, right now, and will run on my box right here. And to the host OS, it looks like just a regular application. Your image, your sort of linked image, looks just like an application. So from the paper that Claudia's guys have published, or not yet, I think, I'm not sure.
Usenix is next week.
Next week, yeah. So next week there is a paper coming out, which again, I highly recommend, you know, keep an eye on it. But I was given a preview of the paper, so here's the stuff I stole from it. So this is OSv manifesto. What do we want from something like OSv? Well, we want them to run existing Linux applications because we really don't want developers to re-architect their applications. We actually want it to run faster, and this is an amazing bit to me because at the end of the day, this is a virtualization-based solution. And the typical question you ask about virtualization-based solutions is like, how much slower would it run? No, this thing actually runs faster, and I will explain why. So make boot time essentially about the same as exec time. So starting an OSv image would be completely equivalent to just starting a JVM image, right? You know, on the same host. Explore APIs beyond POSIX because, you know, POSIX is a little bit constrained. So if we can, you know, lift those constraints, you know, we can get additional performance. and stay open. So it is amazingly a very open source, community, very welcoming one. Very active development mailing list. All of the development happens on GitHub. I could not have been happier about, sort of the state of the community. Again, I come, so like my job is at ASF, Apache Software Foundation. I typically brag about how good we have it at ASF. OSv is actually a really good open source project. But forget about all of this. Let's actually look what's inside. So what's inside, essentially, you get an image, and that image, think of it as static linking. You all know what static linking on Unix is, right? Instead of dynamically getting bits and pieces of the file system, you basically, at a link phase, take all of that same bits and pieces, put it into a single image, and that is now a completely independent from anything else on your file system image that can conceptually run on sort of any Linux kernel. Something like that happening here as well, but instead of linking an image that happens to be an executable for Linux, you're actually linking an image that happens to be an executable for KVM or any kind of virtualization solution. It's a full-fledged sort of like virtual OS kind of an image. So inside that image, you basically have C++ kernel code, and it's pretty amazing, what OSv does with C++. So like if you're a C++ geek, I definitely recommend you take a look at it. But at the end of the day, everything, your kernel, your application, all of your libraries, everything sits inside of the same address space. So it's a huge address space. Think of it as a single, page. Then everything is in there, right? And by the way, of course, it means if you do pointer arithmetic incorrectly, you can totally kill the kernel. But it doesn't really matter because kernel is per application. So if you kill the kernel, what it effectively means is just your application per adopt. Well, that happens to an application from time to time. Again, for managing block storage and for managing networking, there are layers, ZFS is for block, and TCP IP stack, which I will get into the details, that are implemented. Again, ZFS is leveraged, TCP IP stack is implemented from scratch. The actual hardware devices from your host operating system are being given to the guest operating system through the magic of Vert.io, which is pretty performant. So it's not like you're emulating everything. You're actually getting quite a bit of leverage from the assisted virtualization. And then there is a bunch of threads. That's it. Just a bunch of threads. Some of them are kernel threads, some of them are user threads. There's absolutely no distinction between threads. In fact, the good thing is your system calls, the dreaded system call that we all have been optimizing for, now becomes a library call. There's absolutely no cost because it's the same address space. And there's quite an interesting sort of set of optimizations of how you can leverage some of the user space threads to do typically sort of kernel level, work. But that's essentially what you get when you compile and link an OSv image. Then you give that image to QEMU or to Zen sort of thingy, and it just schedules it on your CPU. And at that point, that image has full access to all of the CPU capabilities. And that's actually quite powerful. Because at that point, it can use anything that the CPU has without any regard of whether it belongs to a kernel space or a user space. So let's say MMU. So MMU is typically reserved for the operating systems, to manage page tables and whatnot. Here you can actually leverage it in your application. And again, I will show you how OSv guys are leveraging it in optimizing Java. But with all this goodness, is there like absolutely nothing it cannot do? No, there's actually a few things. So first of all, because it's a single Unikernel, there is absolutely no fork allowed, right? Because there is no such concept as forking, and there is no processes, right? It's a single process. I believe that there are some, ideas about implementing fork outside of the hypervisor, but again, I'm not sure whether that has seen any light of day yet. But today, it's a fair restriction, no forking. No process isolation because there are no processes. So all of your processes are essentially threads, right? That's the concept, the rough concept. And this is the least amount of drivers, device drivers you ever have. So because ultimately what you want out of your host OS is to be a glorified device driver for your hardware, and then everything that's application specific you do in the OSv. So with all this excitement, what's the performance implications? Well, like I said, quite amazingly, the performance actually improves. So on network-intensive applications, unmodified applications, and again, you can actually run an unmodified application by statically linking it inside of this, OSv image. There is one slight catch. because everything is done through the dynamic linker, your application needs to be built as a shared object, and it needs to have an entry point. So as opposed to just being a elf with like main. But if you do that on unmodified application, you get 25 performance gain through output, which I believe was measured on memcached. Again, pretty popular, sort of C, C++, not even Java application. 47% decrease in latency, which is again nothing to actually sneeze at. For non-POSIX API use, if you're actually willing to rewrite some of your applications, you get actually quite a drastic performance increase. On the compute-intensive applications, your mileage may vary, because obviously you are now constrained by the hypervisor, right? And if all that your application does is compute, I don't think you can expect any kind of performance improvements from just about anything. I mean, it's essentially burning CPU cycles. But let's actually very quickly just give you a bunch of previews, right? Most of this is pretty deep, so like I can talk, for maybe 5-10 minutes about each of these slides, and I'm sure again Don and Dor can talk even more. But let me just very quickly explain to you where this performance improvement comes from. So on the networking side, the biggest reason that we see those numbers is that OSv has a TCP IP stack that is fully optimized for running just a single application in the same address space. In fact, they were one of the sort of few people to implement Van Jacabson's net channels, which is essentially a pretty simple idea. If you look at a typical TCP IP stack architecture in an operating system design today, you basically have, packets traversing it in two directions, all the time. So there is one direction from the application side. From the top, your application can call, send and receive, and then, stuff goes down, to the level of interface, network interface. But then there is also, interrupts coming from the interface itself. So like packets are arriving, and, the TCP IP stack needs to be in the business of processing those packets. So you basically have locking, because, it uses common data structure at every single level. So like all these, calls are completely totally interacting with each other. If you implement channels are essentially, you get a packet and you basically create a particular channel that is specific to that type of a packet, and you start, just shuffling them back into the application. First of all, you reduce locking. So all of a sudden, you just essentially lock at a single place rather than, multiple places. But second of all, which was amazing to me, because you now reduce the amount of processing that's happening, your packet has a higher chance, actually way higher chance, of not being lost from decache of your CPU. So basically, the way it goes is, you get a frame from the NIC, and by the virtue of acquiring it, and doing some initial processing in it, the data ends up in the decache. And because it's so quick, to traverse that stack in the other direction, the data doesn't actually leave the decache of your CPU. So when the application is about to actually process that data, the data is still cached. So that's another reason that there is quite a bit of performance improvement. So another optimization is, if you think about memory management in typical Unix, well, you have OS memory that is, segregated between different processes. Within each process, maybe it's JVM, so it has its own heap. Okay? So with OSv, I mean, the first thing that comes to mind is like, well, now it's a single process, so all of the memory sort of belongs to one single process. But a very cool trick that they do then is, well, but then if all that you're running is JVM, let's actually completely flip the relationship between the two. It's called JVM ballooning. So let's actually completely flip the relationship and say all of your memory from now belongs to the JVM, but an operating system has an option of creating an object, essentially a completely opaque object that all the JVM knows about. There is a reference to that object, hence it cannot be garbage collected. And at that point, operating system, because again, remember, single address space, very cool. At that point, an operating system can actually use the memory assigned to that object for whatever purpose it needs. So these completely flip the relationship between the memory management inside of a kernel and a memory management sort of in your application. All of the memory belongs to the application, no more X and X. It's just from time to time an operating system would essentially borrow bits and pieces of that memory. Another cool thing that goes back to me talking about CPU capabilities now available to the application, what happens when a reference in Java changes? Well, if you have object 1 that has a reference to object 2, if you basically erase that reference, what you've effectively done, you've modified a bit of memory that belongs to object 1. And at that point, unless you're actually tracking it through hardware-assisted capability, there is no way for a garbage collector to know that that thing got changed. But if you can use MMU, that is typically, again, reserved for managing pages in the operating system, you can actually track it, because now it becomes a hardware event. So anything that's written into that object gets tracked, and at that point you have a way of actually tracking what gets changed, so that garbage collector has an assistance from a table that essentially tracks modifications through the hardware delivered events. I have 5 minutes left. There's way more cool stuff. But I have to talk about Docker, because not talking about Docker this week would put me in a very awkward situation. This is exactly the same picture I showed you when I introduced OSv, but there are a few changes, right? And now this picture actually does represent Docker. So you still have your new microservices code, and you still have your virtual machine and whatnot, but instead of the sort of hardware-assisted virtualization layer in yellow, you now have a common shared kernel. So all containers on Docker, on a single host, essentially share the capabilities of the same kernel, just like OSv images share the sort of virtualization capabilities of Xen or KVM. Now, on top of that shared kernel, what Docker does, Docker basically provides you a layer of essentially jailed file system and virtualized network, that sort of thing. But on top of that, it's kind of like exactly the same. You basically have a statically linked image, but that static linking now happens not at the level of sort of an application itself, but at the level of all the bits and pieces that have to exist in the file system. Is it really just like OSv? Is it different? What is Docker? By the way, what is Docker? Anybody knows? What, like, do you guys have?
A shipping company.
A shipping company. Anybody else? Any other suggestions? What is Docker?
Yes.
What is Docker to you? Because like I couldn't figure it out for a long time. Now I think I figured it out. Yes?
Standardized packaging and distribution.
You're a planted man. Tell me, you're a planted man, because that is exactly right. That is exactly what it is. Docker is not Linux containers. In fact, Docker leverages Linux containers to accomplish exactly what this gentleman said, to achieve a standardized packaging and distribution infrastructure.
So it's like Chef.
No.
It's the new RPM.
That's actually good. It's like RPM.
Exactly. And the reason it's not like Chef, although it could have been like Chef or Puppet, is the socially driven image sharing. So I started with Puppet way back in 2006, and the whole promise of Puppet over CF Engine back then was that we would all have this wonderful community of recipes shared by everybody. So your recipes would be applicable to my environment, my recipes would be applicable to your environment, we would build off of each other's recipes, there will be this awesome language that would let us, safely extend classes. None of that happened. Again, not that it couldn't happen, it's just none of it happened. And to me, this is the quintessential sort of point of a Docker. Docker essentially enables the same thing that GitHub enables. And it's no coincidence that index.docker.io now is renamed into Hub, Docker Hub, at least in my opinion. So whenever you do Docker run, you're essentially pulling off a bunch of images that other people created. Just like when you do fork on GitHub project, you're pulling off a bunch of code that other people created. And a very cool thing that Docker does is that it actually doesn't disclose to you that internal sort of packaging format of how these images depend on each other. And I will explain why it's important a little bit later. But before I go into that, let me actually address one more question that people typically ask me when I talk about OSv. So especially in the context of JVM, we actually had that. We had a couple of companies that tried running JVM on bare metal. Even before that, we had a couple of companies that tried Unikernels and exokernels. All of that failed. So why is it different today? 3 things, and I claim that these are the key things. There may be others, but to me they're the 3 things. So first of all, we've arrived at a point when Intel hardware is fully capable of hardware-assisted virtualization, the same way that old IBM systems used to be capable of way back when, and we all laughed at them and we didn't appreciate them at all. Now we get that on Intel, now we all have it. Elastic infrastructure-oriented architectures, right? What I mean by that is we now have conditioned our developers that microservices are good. So something like an application that is spread into bajillion different pieces that need to be projected into a data center is now a reality. we actually need tools to help us manage those types of applications. And finally, we've got Cloud Foundry. So we actually have an implementation of something that can map into that sort of application infrastructure. So it's partially social, it's partially technological, but to me it boils down to these three reasons. And with that, let me actually give you my vision of elastic next generation data center. So my beautiful vision for that is rows and rows and rows of commodity hardware, like things that I completely replace just ripping out of racks. And by the way, everything is rack provisioned. So instead of buying 1U or 2U or 3U servers and trying to figure out how much memory do I put in there, how much CPU power do I put in there, how much storage do I put in there, I basically have a rack that I can plug drives in. I have a rack that I can plug CPU cards in. I have a rack that I can plug my flash into. On top of all of this, there is a commodity just enough OS that serves as a glorified device driver. It has no state, at least not much of a state of its own, pretty much zero. And today we actually have good examples of such projects. So CoreOS, I highly recommend looking at it, and SmartOS, which has its lineage in Solaris, are examples of something that would let me just manage the hardware, get out of the way, and get everything else done via containers and virtual machines. So all I need from my just enough OS on bare metal, let me do either Docker or OSv. Once I have that, I actually want Docker to be Docker++. I want Docker to do exactly what it's meant for, essentially being this unified packaging, socially driven, shared infrastructure for images. But the backend, I would like to be able to plug it into whatever I want. So today, Docker, obviously supports Linux containers, and that's good. But there's absolutely no reason why the same concept shouldn't be applied to OSv, because OSv is kind of like I showed you. It's very much the same. It's just different combination of the same building blocks. But at the end of the day, if I'm a Docker guy and I'm doing Docker run, and that image happens to have a bit of metadata that describes that that image actually happens to be an OSv image, why should I care? And then, of course, we need to have a GitHub for sharing microservices. Just like we have a GitHub for shared source code, we actually need to have a GitHub architecture for sharing all the bits and pieces of functionality that, again, Puppet and Chef kind of promised us we would be able to do, but they couldn't deliver. Now we actually have an option of doing that via containers and sort of these statically linked images. And finally, it'll let us kill DevOps. I hate DevOps. Like, this is the worst concept ever. I mean, this is not... No, but seriously, like, it's not quite dev, it's not quite ops, it's DevOps, right? What I want from my IT, from my dev, I want to maintain my bare OS. I want them to just make sure that my core OS runs. And then I have my devs, who have a very predictable environment, because anything can be replicated, everything is packaged in predictable containers, and the two sort of never really talk. And if you have a next Heartbleed bug, your ops guys are completely unaffected, because there's no SSL installed on their core OS. Like, why would it be there? Your developers, of course, are affected, but that's their business, because they can fix whatever they want to their layer. Basically, I hate snowflakes. Nothing is ever a snowflake. We need to get to a very predictable provisioning model, and I think microservices deployment architecture is pretty much it. So very quickly, guinea pig so far for OSv. OSv is, by the way, a very young project. So again, like a year and a half, I guess, would be sort of roughly the lifespan. So guinea pigs so far have been memcached, very successful results. Apache Cassandra, again, pretty successful. Redis, that's what the Cloudies guys have done. So I have done a little bit of experimenting with Hadoop ecosystem. So I have, data nodes, I have Zookeeper, thingies, and I'm actually like running out of time, constantly to actually do some meaningful performance benchmarks, but I shouldn't. Speaking of which, I'm actually hiring. So if any of this is exciting to you, talk to me after the presentation. And speaking of which, even if you don't join me as a paid employee, we pay well. Anyway, where do we need your help? It's all open source, right? Just join. Start posting on GitHub. Start sending out pull requests, and just to keep you thinking. Cloud Foundry integration, things that are really super exciting to me, right? It's like, can I do CF push Docker container? It would be awesome if I could. There's absolutely no reason. I think there is no reason I should be able to do that. So, sounds like a good idea. Shouldn't then Docker images be kind of like this intermediate representation for the build packs. Because again, the problem with build packs, at least I had, some time ago, is like, well, the build pack runs, and then a whole bunch of things happen. Like, my application got transformed into something, but I don't quite know what that something is, and I don't quite know how to replicate that something. So if we can actually use Docker, sort of the shared, microservices image repository as a backend for build packs, maybe that's a good idea. I don't know, you tell me. Two-level scheduling in Hadoop ecosystem. I mean, that's how Google sort of approached it, at least for the second generation architecture. So you have, this microservices, container, or OSv-based units. You basically stand them up, and all of a sudden you have your own Hadoop cluster. So maybe that's a good idea. And I guess I'm out of time, but questions?
Well, by the way, really nice talk. Thank you very much. I have to say, I'm really excited about what this means for my Minecraft server performance. Could you comment? You were trying to paint a vision of your next-gen cloud. I think OpenStack was significantly missing from your commentary. And I'm wondering where you imagine the actual capacity management of what stuff gets run where based on what hardware is being used and not being used. Sort of fit into your
Right, so the question is, why didn't I say much about OpenStack? So to me, OpenStack will obviously still exist, right? What I'm talking about is the data center optimized for the microservices-based deployments. There will be a class of applications, just like there's a class of applications that we still need, very classical virtualization for. So like, VMware is, well known for virtualizing your, Windows XP, right? It's like if you still need that, I mean, there has to be a solution for that. So OpenStack, CloudStack, those types of technologies will remain at the level of infrastructure as a service. But my belief is that we as a development community have sort of moved above that layer. So there will be still tasks for which infrastructure as a service is absolutely the right thing to do. But most of the time, the next generation applications that we develop will actually follow the microservices deployment model, where infrastructure doesn't actually factor in. And at that point, you're absolutely right. You still have to have some kind of an orchestration layer. And like I said at the beginning of the presentation, that is completely missing from this talk. I actually hope that that would end up being Cloud Foundry natively. But if there are bits and pieces of CloudStack, sort of OpenStack mixed into that, that may be fine as well. What I'm trying to say is at that point, you're basically having a PaaS as a thing that you actually run in your data center. So your data center starts to look like PaaS. Whereas today, your data center, actually your good data center, still looks like infrastructure as a service. And I think that step will be made in like next 3-5 years. Any other questions? Yeah, sure. Yeah, so multi-core is supported, so the question is what hardware is supported. So it's definitely x86, multi-core is supported, so you can have threads being scheduled on as many cores as you want. I believe that there is a port to ARM in the works. So ARM will be supported pretty soon, hopefully again, open source project, join in, help. But I don't know if there's any other architecture. So Dor, do you want to comment?
Probably more architectures will come, like KVM. We were the one that created the KVM hardware, and pretty much all the architecture, including mainframe, got adopted KVM. So we hope in this case it may happen again.
It's almost like a virtual process.
Pretty much, yeah. Pretty much exactly. I have an old friend of mine, like he is old and he happens to be an old friend of mine. Who used to work at IBM, and when I talk to him about this stuff, he's like, kids, youngsters. All right, thank you so much.